Today we're going to look at surfaces in space. We're going to recognize and really learn how to rewrite equations so that we can see whether or not they are cylindrical surfaces, quadratic surfaces, and then we're also going to look at recognizing and writing and rewriting equations of surfaces of revolution. And it sounds a lot more complicated than it really is. We've already looked at spheres, and we've already looked at planes, and so our next step is to look at cylinders, and it looks exactly what you might imagine it would look like. I'm going to have a circle. This one in this case is on the XY plane, and then I'm going to have a line going through that circle perpendicular. In this case, this line is parallel to the z-axis, and if you were to think about either sliding it around the circumference or finding all the lines parallel to that line that also go through the circumference, then you'll make that cylinder. If you can have your cylinder kind of rolled up like a paper towel roll, then you can unroll it and have a piece of paper, and it's still the same concept. This idea of without loss of generality is something you will hear a lot as you move on in math and you get into more and more proofs. And this piece of paper does not necessarily only have to be defined as x and y in kind of algebraic terms. We can have trig functions, and we can have them have kind of take a variety of different shapes if you imagine folding pieces of paper. So let's look at A, which is z equal to y squared, very reminiscent of a parabola, right? So I have a parabola where my y is squared, and then I'm going to create that. In this case, I guess I would call it kind of a width that comes as I am going up and down through that x-axis. And so we're on that YZ plane. If we kind of fold it a little bit, I have z equal to sine of x. So I have a wave in the xz plane, and you notice in the equation, if I go back, I have z and x in my sine of x, so I'm in the xz plane. I had z and y in the parabola, so I'm in the yz plane. Quadratic surfaces are a little bit longer. They don't tend to be quite this long, but it could happen if everything's out in its general form. So everything's been factored out and all of the like terms have been grouped. Normally it's not quite this long, but they certainly could be. And you have a couple of different types, 6 actually, so a few more than a couple, that you can have for a quadratic surface. You'll have an ellipsoid, so we're going to take all of our 2D graphs and puff them up or out depending on how you position your z-axis. A hyperboloid, either one sheet or two sheets, so that's my hyperbola. Sometimes it's still kind of connected. Think about your paper towel roll that kind of gets squished, or sometimes it kind of looks like two plates. An elliptical cone, elliptic paraboloid, and then the hyperbolic paraboloid, or we usually just call that one a saddle. You can trace them using the same method you did before in the other videos when you were letting some variables be 0 and some variables you were solving for. Or you could remember some of what the general forms look like. So if I have an ellipsoid, I have x squared over a squared plus a y squared over b squared plus a z squared over c squared equal to 1. So very much like when I had an ellipse in my 2D. The hyperboloid of one sheet, you'll notice that I'll have a z missing, well, on this particular graph, but the variable that has the negative, that is the axis that the hyperbola is revolving around, right? So this has the negative z in this example, so I am revolving around the z. Had it been the y, then we would have had it laying down and revolving around this. Notice they're both equal to 1 and that everybody is squared, x, y, and z. Two sheets, again, everybody is squared, but I'm going to have two negatives, split this piece up. The one that is positive is the one that you're going to be intersecting through. And then I have an elliptical cone. Now this one is an elliptic cone equal to 0. So sometimes you'll have that z or whoever is negative on the other side. And the axis of the cone corresponds to the variable who is negative. So again, the one that you're revolving around, or in this case it kind of looks like it's teetering around, is the one that's negative. And then we'll have our two paraboloids. Kind of looks like a badminton birdie. I have x squared over an a squared plus a y squared over a b squared equal to a z, though. Notice that this is the only one that we have seen so far that didn't have all the variables squared. The one that is raised to the first power, that's who you're revolving around. So here z is to the first power, so z is who we're revolving around. And then here is my saddle. Again, both of these squared, I have the subtraction in between, and only one is raised to a single power. Let's look at this example. When you're classifying these guys, when you're rewriting them in order to classify them, it will be a pretty familiar process from when you were in 2D. You may or may not have to group variables. You may or may not have to complete the square. But it's about organizing it so it will match one of those formulas, and then you can begin to recognize them. Now, you can also start to kind of, as a little bit of a cheat, is look at the variables. All of my variables are squared. I am not dealing with a paraboloid, right? So because everybody's squared. I have one that has a subtraction, two are positive. Now that can certainly change as you go through the process, but I'm probably not dealing with an ellipse because of that negation, and I'm going to have to do some division and some moving things around. Let's go ahead and divide everybody by a negative 12 or positive 12. Either way would have been fine. If you divide by a negative 12, I'll have this negative 1 over here so that when I bring it over to the other side, it's equal to a 1. And I see that, oh, I have two negatives now because I had to divide by a negative 12, right? So they flip. Sometimes that happens. And I can go over to the formula sheet and see that this has to be a hyperboloid of two sheets because I have these two subtractions in here, right? These two negations. Some are longer than others. You can use the trace idea of letting things be equal to 0 and kind of sketch those using that method, or if you're familiar with a 3D grapher, you can certainly use that to help you out. Surfaces of revolution is kind of taking that same process where I have this one equation that I'm going to revolve given a specified radius around a given axis. The generating curve is going to be y equal to an rz, or that radius function, if you're in yz, and of course that will change if you're in x, y, or xz. If I have this graph that's revolved around the z-axis, so that means that I'm going to be talking about my radius of a z, and then I'm given a circle that's x squared plus y squared, I know that this needs to be a radius in a z form, right? So I need something written where it's some kind of expression that involves z. And then I can find all of the different values. Those are our other radius functions. Let's find the equation for the surface of a revolution formed by revolving first the graph of y equal to 1 over z, and then we're going to look at the graph of 9x squared equal to y cubed, and now we're going to be going around the y-axis. So if I'm revolving the graph of y equal to 1z, that's my radius function, then that, if my radius function is written in the form of z, then it's r of z. And if it's the expression is using z, then the other two have to be over here. I have x squared plus y squared. Now all I need to do is take that 1 over z, since it's already written that only z is in the expression, right? So 1 is isolated. I go ahead and sub it in and square it, and we're all good. For 9x squared equal to y cubed around the y-axis, well, I'm going to need, if this is going to be my revolving, I need this to be around y, then I need r of y. So I'm going to have to rewrite this that it's x equals to, and then whatever my expression is that involves the y. When you work through that process, here's your r of y. And if there's y here, then I know that my other one has to be x squared plus y squared, because we're revolving around the y. So there's my circle. I'll plug in the 1/3 y to the 3/2 and square it. And there's the equation of the surface. So it's not really all that bad. We're going to go ahead and look at some examples. Some of the examples I've worked out ahead of time just to save you some time in the video, but the beginning ones we're going to work through step by step. So it says match the equation with its graph, and here's my equation. Of course, that doesn't match any of the formulas that I had, and they gave me some graphs to choose from. So I have this negative y in there, and I have a x squared and a z squared. Nobody's to the first power, so I'm thinking he's probably out, and I have a negative, so this is probably out. And everybody's squared, so that one has to be out. So I'm probably looking at something that looks like this. So let's start this process. I got 15x squared minus 4y squared plus 15z squared equal to a negative 4. Well, I know I need this to be equal to a positive 1. So if I divide everybody by a negative 4, I get now a negative 15/4 times x squared plus a y squared minus a 15/4 z squared. And there's my 1. And I'm actually pretty much done right now. Now my y is positive, and I know what you might be thinking. Let's go back to our formulas. All of these had no constant up at the top, right? So it was just a 1z squared over a number. That's what we have here. What we're going to do, so it kind of matches a little bit nicer, is we're going to take this multiplication and turn it into division. So this, well, let's put the y squared first since it's positive, and then I'm going to say negative. I'll have my x squared up top, and instead of saying multiply by 15/4, I can say divide by 4/15. Instead of saying negative 15/4 times z squared, I could say negative z squared divided by, again, the same thing, 4/15. And now this matches my formula. I have the two negatives. Let's go back to our formula. And it must be this one of 2 sheets, because I have my 2 subtractions. And the one that is positive is what we are revolving around. And my positive is a y. Well, I only have one to choose from, so it must be this one. And notice we're revolving around the y here. All right, so you can leave it as a constant out front here. You can have that, coefficient. You don't have to go through this process, but it might be a little bit easier to see which matches. Let's look at another one. It's almost already set up. I have 0 equal to a 4x squared plus a 9z squared minus the y squared, and there's only one that is set equal to a 0. If you remember, it would be this one right here, my elliptic cone, and I have the one negative, and that's what you revolve around. That's what I have here. So I'm talking about something looks like this. X squared minus a y plus a z squared. All right, so y is to the first power. So I know I am definitely dealing with either the saddle or the elliptic paraboloid. I have the subtraction. So, well, that would be x squared plus z squared equal to a y. So I have a plus, and I don't have the subtraction. So I am looking at this one. So it must be this one right here. A little bit more interesting, right? One of the longer ones. I have this one kind of started so that we can go along a little bit quicker. This is just my original one written with this 36 moved over. I also took my x's all together, my y's are all together, and then of course my 1z that I have there, because I'm going to need to complete the square. In the formulas, they're set up if you're centered at the origin. Of course, you can still slide these guys by having x, y, z plus or minus something in, and then have that quantity squared. So I'm going to factor out the 16. So I have x squared minus 2x, and of course I have to start my process for completing all the squares. I have my blank. Factor out the 9 here. Sometimes you can leave the constant over on the other side. You probably would be able to use it. I like to just get it out of the way because I'm going to be adding things in anyway, and it will work itself out. Blank and a blank over here. So what gets put in order to complete the square? You take your b value, you divide it by 2, and you square it. That's what gets added in right here. So I'm going to put the 1 in here. And then over here, this would be a 4. And so I put the 4 over here. But I put the 1 here and the 4 here. But if you were to distribute, it's not a 1, it's a 16. It's not a 4, it's a 36. So you don't put 1 and 4, you put 16 and 36. This will take care of that negative 36, and now I have it set equal to 16. We are getting closer. All my coefficients are positive, so we are probably not looking at these. Let's go ahead and divide everybody by a 16. That divides to 1. This will be 9 over 16. This divides to 1. This divides to 1. And we can use the same trick as before. Instead of saying multiplying the quantity y minus 2 squared by 9/16, we can divide by 16 over 9. And I have an ellipsoid. Let's now start to look at finding surfaces of revolution. And I have 3 examples. I have them all pulled up already. Find the equation for the surface of revolution generated by revolving the curve in the indicated coordinate plane around the given axis. So I have the equation of the generating curve. Z is equal to 4y. I'm in the YZ plane, right, because I got Z and Y. I want to go around the Y-axis. So if the axis of revolution, that's what's going to be the R. So I want to have the radius go around that y-axis. So I have x squared plus z squared equal to the radius y, right? R of y, that squared. So I need the generating curve to be something equal to something else with y. So it's already good to go because it's z equal to 4y. So that is R of y. All I need to do is plug it in and square it, and I have x squared plus z squared equal to 16y squared. Now I'm in the xz plane, right? I got x and z. I want to go around the x-axis, so I'm talking about R of x. So over here it has to be y squared plus z squared. I need this to be something, that other variable, z equal to a bunch of stuff, and then the x is there. So I just need to get this 10 off. I'll divide everybody by a 10. Take this, plug it in for R of x, and square it. So I have 100 times the quantity 100 minus x squared, distribute, and I'll have y squared plus z squared equal to a 1 minus 1 over 100 x squared. We can clean it up, add the x squared over to the other side. You can also multiply everybody by 100. Either one is fine. One more. I have x is ln of z, so we're in the xz plane. We want to go around the x-axis, so I need R of x. So this needs to say z equals, and then something with the x. So I'm going to need to rewrite this. If I raise them both up from the e, I'll have e to the x. E and ln undo each other, so that's equal to z. That is my r of x, and e to the x times e to the x is e to the 2x. And that's how you recognize some cylindrical and quadric surfaces and surfaces of revolution.